Imagine a force so powerful, it shapes the destiny of the entire universe, a mysterious energy, invisible yet everywhere, stretching the very fabric of space. This force doesn't pull things together, it pushes them apart, and against all logic, it's making the universe expand faster and faster. Today, we're decoding one of the greatest enigmas in science, dark energy, the invisible engine of expansion. The story begins in the late 1990s. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search, were mapping distant exploding stars called Type Ia supernovae. These supernovae are nature's perfect cosmic mile markers. They all shine with nearly the same brightness. By comparing how bright they appear to how far they are, scientists can measure how fast the universe is expanding. But what they found defied reason. The supernovae were dimmer than expected. That meant the universe wasn't slowing down. It was accelerating. Some unseen force was overpowering gravity. A force driving galaxies apart faster and faster through time. They called it dark energy. And suddenly an old equation came back to life. Back in 1917, Albert Einstein had introduced a mysterious term in his equations of general relativity, the cosmological constant, denoted by the Greek letter L, lambda. He added it to balance the pull of gravity and keep the universe static, a cosmic counterweight. But when astronomers later discovered that the universe was actually expanding, Einstein removed it, calling it his greatest blunder. And yet, decades later, that so-called blunder might have been the right answer all along, because the cosmological constant perfectly fits the description of what we now call dark energy, a property of empty space itself that pushes the universe apart. Empty space isn't really empty. It seethes with invisible energy, hidden deep in the vacuum, and that energy could be fueling the universe's accelerating expansion. Here's the cosmic conundrum. When scientists add up everything we can see, stars, planets, gas, dust, it accounts for less than 5% of the universe's total energy. About 27% is dark matter, invisible mass that holds galaxies together. But the largest piece, nearly 68%, is dark energy, an unknown pressure blowing the cosmos apart. Our universe, it seems, is a vast cosmic scale that doesn't balance. The equations for matter and gravity no longer add up. To truly understand the universe, we must confront the invisible and redefine the very nature of reality. The first big idea comes from quantum physics, that empty space isn't empty at all. Every cubic centimeter of vacuum is filled with fleeting quantum particles that constantly appear and disappear. A restless sea of energy. We call it vacuum energy, but when physicists calculate its strength, the results are absurd, about 1,120 times greater than what we observe. That's a 1 followed by 120 zeros, the biggest mismatch in physics history. Somewhere, between quantum mechanics and cosmic expansion, something crucial is missing. Another theory suggests that Einstein's masterpiece, general relativity, might not be the full story. Perhaps gravity behaves differently across vast cosmic distances. Maybe what we see as dark energy is actually a subtle twist in the geometry of space-time itself. If true, it means we've misunderstood gravity, and might need a new law of physics to describe the universe. And then there's the most chilling hypothesis of all, phantom energy. If dark energy's strength grows over time, it could one day overcome all forces that hold matter together. Galaxies would scatter, stars would rip apart, planets, and even atoms, would be torn to shreds. A cataclysmic end known as the Big Rip. We're not there yet. But the idea reminds us just how little we truly understand the universe we inhabit. So how do we study something we can't see or touch? Astronomers turn to light, the one messenger that travels across time. They use distant supernovae to measure cosmic expansion, the very data that first revealed dark energy. Then came the cosmic microwave background, the faint afterglow of the Big Bang. By studying its tiny ripples, mapped by satellites like WMAP and Planck, scientists determined that nearly 70% of the universe is made of dark energy. Now, a new generation of missions, like ESA's Euclid, NASA's Roman Space Telescope, and the Vera Rubin Observatory, aim to probe dark energy with unprecedented precision. They'll map billions of galaxies, trace how cosmic structures grow, and maybe, just maybe, reveal the true nature of the dark cosmos. Dark energy isn't just a scientific puzzle, it's an existential one. If it remains constant, the universe will expand forever. Galaxies will drift beyond reach. The night sky will grow darker, colder, and emptier. Billions of years from now, even the nearest stars will vanish from view. Future civilizations might never know that other galaxies once existed. In that distant future, the universe will be vast, but lonely. A cosmic isolation born from the very force that gave us light, life, and time itself. Dark energy defines our past, shapes our present, and will decide our ultimate fate. To understand it is to understand the universe's soul, and perhaps our own place within it. If this journey through the dark side of the cosmos sparked your curiosity, hit like, subscribe, and join us as we continue decoding the mysteries of the universe.